So thanks everybody for joining us. My name is Mike Hayes from Tyndall National Institute. So it's my pleasure to open up today's webinar on use cases, real world use cases related to energy harvesting. And this is the second of probably 3, maybe even 4 webinars that we plan to hold in relation to this. So this is the running order for today. So we'll start with a brief introduction to the speakers and maybe a little bit of context as to why we're presenting this today. The main body of the presentation will be around 6 real-world use cases that we have come across and enabled through various types of activities, such as the transnational access activities that I'll describe in the next couple of minutes. And as Nicholas said, we finish up with some Q&A as well towards the end of the presentation. Okay, so we'll switch from presenter to presenter as we go through each of the use cases. I'll cover the first one, then I'll pass on to my colleague John Flannery for the second one. So let's get on with it then. So the 4 speakers you'll hear today are myself. So as I said, my name is Mike Hayes. I'm the coordinator for Enables. I also manage a group called ICT for Energy Efficiency at Tyndall, where we're focusing on solving the Power IoT challenge. How do we make these wireless IoT devices last longer for many applications? Then be followed by my colleague, John Flannery, who's a principal packaging engineer at Tyndall. John brings over 25 years of both industry and research experience and expertise in embedded power solutions in what we call PSIP and power SOC solutions. So that's power solutions in package and power solutions on silicon. Okay. Our third speaker is from Fraunhofer IAS. So this is Peter Spaes. He's the group manager for the Integrated Energy Supplies group there for integrated circuits from the Department of Self-Powered Radio Systems. And he's a business field coordinator for IoT systems. And our final speaker today is Gerd van Boegel from Fraunhofer IMS. So he's the head of the business unit industry at the Fraunhofer Institute for Microelectronic Circuits and Systems. And his main research topics are things like IoT, energy harvesting, sensor, transponders, and RFID. So a little bit of context and a bit of background first. So what's the problem we're trying to solve here? And the big challenge we have out there is that it's envisaged that by the year 2025, which is only 4 years away, we're going to have up to 1 trillion IoT devices in our world. Many of these being wireless IoT edge devices. Sounds like a crazy number, but when you think about it, it's probably equivalent to maybe 100 sensors for every person. So when you think about the sensors in your clothes, in your house, in the infrastructure that you have in your school, in your smart mobility applications and so on, maybe it's not too far off. Certainly several tens of sensors per person sounds to be a reasonable number. In any case, it's going to be a very big number. And what we see is a need for the elimination of battery replacement where possible. And how do we do this? We find ways to reduce the power consumption of devices, and where possible, we develop energy harvesting solutions. That is, we take ambient energies and we convert them to electricity so that we can use this as an alternative power source. How do we do this? We do this by bringing together various types of people in our ecosystem. We get them to work collaboratively and concurrently together to develop applications or develop solutions which are very much application orientated and optimized towards the overall system that we're trying to develop. So this involves getting academic and industry developers of energy harvesting components and systems and the people developing the IoT devices to work together. We need to accelerate and optimize the development of parts and systems. And one very important sub-theme of this is that the parts that we develop should be standardized and interoperable so that they are reusable and reconfigurable easily for various stakeholders for present and for future applications. So what are we doing about this? In Enables, what we are doing is putting together an ecosystem which comprises a 5.2 million euro research infrastructure project. And it's all about developing self-sustaining energy solutions to power the Internet of Things based on energy harvesting and related technologies. So this includes energy storage, power management, and indeed system integration. So these are the icons that we use: energy harvesting, energy storage, micropower management, and system integration. And the kind of activities we have in Enables are what we call our transnational access program. And this is giving the world access to leading laboratories and leading expertise in Europe. So within our Enables ecosystem, we have a body of over 130 researchers available and over 2 billion euros worth of research infrastructure available for people from academia and industry. We also have some of our funding available to do between the 11 partners and Enables what we call JRAs. So this is joint research activities, which is very much guided by the needs that we see out there and the opportunities we see there, particularly from activities such as we're doing today, interacting with various types of stakeholders and understanding what are the opportunities out there, what are the challenges, what are the applications that people envisage. As I mentioned previously, it's very important that we create standardized and interoperable parts. So this means that the libraries, the simulation models, and the tools that we develop have this standardization and interoperability features. And we also see Enables as being a key element in developing what we call a starting community, building a continuous, sustained community of people working together to solve this IoT challenge. What you see there at the bottom of the screen are the various methodologies that we have supporting Enables. So we have simulation tools. We create various types of standardized libraries and metrologies. And then we also come up with tools and methodologies for optimizing the system level behavior of our various components. So this is kind of a visual representation of what Enables is all about. This is us trying to power the Internet of Things. These are the various methodologies we have. These are the 11 partners we have in Enables. So 4 of the 11 partners, it's actually 6 when you consider CEA and Fraunhofer are actually 2 different divisions. So we have 6 of the partners providing access to our infrastructure and our expertise. The other 6 remaining partners are various universities and research institutes in the UK and in Germany and in Italy, working together with us on these joint research activities and building this Power IoT ecosystem. And within Enables, we have what we call technology push and technology pull. So the JRAs, the joint research activities, is our technology push. This is us collaboratively developing technologies and pushing it out into real life applications. But then this is coupled with what we call technology pull, talking to people in industry and academia, understanding what are the applications and the needs out there, and then pulling from their needs to try and take our technologies and translate them into solutions for the problems and the opportunities that they have out there. And what you see here on the right-hand side then are the 4 kind of enabling technologies: energy harvesting, energy storage, micropower management, and system integration. And just some images there of various tools, various types of hardware platforms, various types of systems, components that we're developing, and also just giving an indication of the types of access infrastructure that we have available to us. Okay, so the Transnational Access Program itself then is a free of charge instrument that's available to everybody. So the European Commission will pay us for any work we do under the Enables TA Transnational Access Program. So this is your opportunity to gain access to the people and the equipment that I've talked about there, doing things like simulation studies, paper studies, state-of-the-art reviews, maybe some early prototype development or characterization of materials or devices, or maybe doing some system optimization or metrology experiments. We have access. We've also created what we call a virtual access database of real-life vibration energy sources. And this was created by combining databases from 2 of our partners from Southampton and Perugia. And we are now adding to these databases accordingly as we gather more information and we do more joint research activities and transnational access programs and further enhance the database. It is open to everybody, industry and academia, anybody doing research work, development work, system integration work, and so on. And you can find some further details on our website there if you're interested in subscribing to Enables and hearing about our activities, such as today's webinar. What are the outputs from Enables? What type of activities we're involved in, and so on. Paul Rosengrave, who is hosting today's webinar, is also available if you want to find out a little bit more about Enables. So I'm not going to go through much detail in the next couple of slides. This is simply to give people an indication as to the nature of energy harvesting and the nature of the power consumption of IoT devices. Anybody who's worked in this realm will see that the power consumption of these devices varies very much depending on what the device is doing. And these devices are typically wireless IoT edge devices, which have things like sensors, transceivers, maybe localization systems, in some cases, actuators, displays, interfaces, and maybe some lighting indicators as well. So depending on how we mix and match these and the operation mode we have for these, the power consumption varies significantly. And that's what we're showing in the right-hand image there, that accordingly, as we go through various types of sensing and transceiving, and indeed actuation, you'll see that the power consumption varies quite considerably. So it's very important to understand the average power, the peak power, the sleep current, sleep power, and the overall average power, and the overall energy used in a given sensing cycle. This second slide here kind of gives you an appreciation for the implications for the operation mode. In this case, we're looking at a GPS tracking device. So you can see here, depending on whether we have mode 1 up to mode 4, the power consumption varies from 2.5 milliwatts up to 17 milliwatts. And just to give an appreciation from an energy harvesting point of view, we give you an idea then as to what the relative size of a solar panel would be required to power such a device. So you can see there, if we're just doing 2 measurements per day, we need a solar panel 7 centimeters squared. If we want 4 operation modes per day, it goes up to 47. So significant implications there for this. This is a busy slide. All I'm going to point out here is that we have different types of ambient energies available to us, things like photovoltaic or light energy, thermal energy, vibrational energy, and also there's a lot of work underway in terms of RF energy as well, and inductive energy transfer. The main thing to look at on this slide here is the kind of typical output powers. And you see these powers vary quite considerably from, a small number of microwatts up to tens of milliwatts. It really depends on the amplitude of the ambient energy source. How big is the temperature gradient? How much light is shining at a given time? What's the acceleration and the amplitude of the vibration source we have, and so on. Okay, so you can study this in your own time offline, or come and talk to us if you want some more information regarding these various types of ambient energy. So that's the introduction over. Let's talk about the first use case, and I will introduce this one. This one is actually being done by ourselves in Tyndall. It's been managed by one of our PIs. His name is Jerry McGlinchey. He's been working with a Swiss SME called Swiss Airtainer, and they're in the business of supplying and servicing what they call ULDs, Universal Load Devices. So these devices should look familiar to most people. We all remember the good old days when we used to hang around in airports. These are the kind of devices we'd see being loaded and unloaded onto planes. They are used for obviously cargo transportation, but there are people who are particularly interested in understanding what happens to these cargo vessels during their journey. So as you can imagine, particularly if your items are very expensive, and if they are sensitive to the environment in which they've been transported in terms of the temperature, the pressure, what kind of vibrations they would have seen there, a lot of people would pay a lot of money to understand what kind of a journey their device had. And for example, Swiss Airtainer do a lot of work in the pharmaceutical and medical device segment. COVID vaccines will be a very good case in point, for example, at the moment. So these ULDs are regulated by IATA, which is the International Air Transport Association, and each of them has a packing list, and the environment of these devices is very often carefully controlled for various types of regulatory requirements, for example, for the pharmaceutical market. So in this case, what we're doing is we're trying to understand, if we try and put some wireless sensors on such devices, what are the implications for the power consumption, and indeed what are the opportunities for energy harvesting, depending on the type of things that we're monitoring, the type of data we're collecting, how often we send the information, and so on. But the idea is that these ULDs have some sort of intelligent systems which are to some extent able to self-monitor, send alerts based on various things happening in real time, If they see deviations versus customer expectations, they can report them, and they can also give some sort of a live or historical report of the journey that the particular contents had. Now, of course, the battery for the sensors that we use here is important. Ideally, we would like these batteries to be at least 5 years plus, but typically, according to people like Swiss Airtainer, the battery life is typically 18 to 24 months. So, for example, if they're doing servicing every, let's say, 2 years or every 3 years, that means that they have to go in between service intervals and change the batteries. So that's actually a significant cost, and it can actually cause problems as well if data is lost, if they don't get to the batteries on time. So I think one can see quite easily there the value of energy harvesting to make these batteries last longer and improve the service level and reduce the life cycle costs associated with this. Here's a visual graph indicating the kind of system that we have within the ULD and the infrastructure around it. So in this case, we're looking at things like the monitoring the geographical location of the ULD, the kind of parameters that they measure, things like temperature and humidity. And they're also interested in things like acceleration, pressure, sound, and they may also be looking at electrical power signals as well. This can be useful contextual information for them to understand where the device is and where in its journey it is. Okay. In terms of, for example, a plane being, for example, in an airport, you know, there's lots of sensory data in the infrastructure around it. So we have things like RFID tags, we have GPS systems, various types of mobile networks, also Bluetooth networks available. And then we also may have other types of wireless infrastructure, for example, a local area or long range wireless access networks as well. And all of these networks are going to be constrained by the actual power that's available. So it's important to understand what these networks are, what information can be extracted or what information can be shared based on using the collective of these data networks and what the power consumptions are. So final slide on this first use case. The challenges here are trying to understand how do we minimize the power consumption of existing and emerging technologies based on the various components we talked about there, the sensors, power management, transceivers, and the processors. And I think one big opportunity that's there is using this whole idea of context awareness, turning on and turning off sensors as needed, using the data around you, using current data, using historical data to understand if there are any anomalies during the journey or not. Also, we plan to try and understand the power requirements of current solutions. And last, by no means least, we also want to understand during what parts of the journey are there ambient energies available, and can we make use of these ambient energies when they are available to further extend the battery life. At the moment, this transnational access program is underway. We've agreed a work plan, and hopefully in a future webinar or a future Enables event, we'll be able to tell you more about the outcome for this. Okay, so that's me. I'm now going to pass you over to my colleague, John Flannery. I'm going to stop sharing and let him share his slides based on the second use case. Over to you, John.
Okay, thanks, Mike. Just getting my share organized now. Where am I? Right, hope you can see my screen there now.
Yes, we can.
So good afternoon, everyone. I'm going to present some of the work that we're doing in one of these Enables transnational access programs. This project on smart wound care was originally introduced by Mike in a previous webinar, but today I'm going to give a slightly deeper dive into the area. And the project was proposed by a Dutch-based company called Icon Global Innovations.
John, could you go into presenter mode there?
Yeah, I thought I was in it.
Not on my screen.
We're seeing a preview of your slides, John, so you just
Okay.
need to hit.
Right.
I'd say try and hit the screen icon.
I'll stop share first. Is that any better?
Just click on display settings And there you should be able to swap.
Middle,
Place
yeah.
everything this.
Yeah.
Middle top, yeah.
New share.
No, where's
Oh,
the
this one.
the,
Yeah.
the presenter view? There, that's
Perfect.
it.
Yeah,
Okay.
we got it.
Right. Sorry about that.
Okay.
So the motivation for smart wound care, well, it's based on the fact that traditional wound dressings are passive, and their primary role really is to keep the injury site sealed, sterile, and protected. But one of the features of this is that the dressing always needs to be removed for wound inspection, and this act in itself can disturb and even delay the healing process. But in contrast, smart wound care is generally understood to be based on active dressings, which can sense wound parameters without removal, and therefore lead to accelerated healing and better outcomes. So for many applications, having a reasonable dressing life is important in order to optimize the number of wound inspections and to minimize the need for battery changes due to the healing process. So part of the Enables expertise is an analysis of the potential for both energy harvesting and smart power management to extend battery life in these applications, ideally extending it from days out to weeks. So we had a number of discussions with the client when we were refining the project, and we settled on the following areas of interest. First, there's great interest in the area of power consumption for any sensors that would be used as part of smart wound care. Then we discussed the possibility of integrating electrical stimulation to enhance wound healing. Another particular area of interest was to investigate opportunities for thermal energy harvesting, which would enhance battery life. And the final point was the integration of a suitable low power wireless system. But from these discussions and the limited scope within a single TA, it became clear that the main focus of our study would be in points 2 and 3 here, being electrical stimulation and the investigation of thermal electric generation harvesting. So what is the role for electrical stimulation in wound healing? Well, in fact, electrical stimulation has been used for many years in the medical field, with its main application being in muscle and nerve stimulation. In muscle stimulation, it's used as an aid in rehabilitation from injury, as well as being used for targeted muscle training and massage. And in nerve stimulation, it's probably most familiar used as TENS for pain management. But eStim has also been used as an aid to promote wound healing, where it has been found to promote cellular movement in and along the edges of a wound. And there are many, mostly small-scale clinical trials reported in the literature using a variety of electrical parameters. These images here on the right show some of the parameters reported on, ranging from low-level DC current to various types of monophasic and biphasic AC pulsed waveforms. These trials all report generally positive outcomes for wound management, but no strong preference for any particular waveform type, indicating that more research and larger clinical trials would be required. So to try and understand how stimulation could aid in wound healing, we have the concept of the skin battery. So in healthy skin, the normal migration of ions creates potential difference through the different layers of the skin. And at the edge of an injury, the small voltage creates what's called the current of injury, which can be measured up to a few microamps. This small field is believed to aid cellular motility around the wound, allowing it to heal from the outside edges in. And it's believed that in the case of large or difficult to heal wounds, this skin battery can be enhanced by the application of an external stimulation. So here's an example of one of the many waveforms reported in the clinical trials. It consists of 132 microsecond pulses of about 30 milliamps with a 1.7% duty cycle. So very simply, if you look at the power in each pulse, it represents about 750 milliwatts. So with that duty cycle, that represents an average power of about 13 milliwatts. And if we assume we generate that signal with a DC-DC converter with an efficiency of about 80%, we need an input power of a not insignificant 18 milliwatts. So what type of battery could be used to power this? Well, if you look at the requirements for batteries for body-worn applications, there are many factors to consider, such as energy capacity, pulse current capability, moisture resistance, comfort, storage, flexibility, and even how you dispose of it at the end of life. And these are two common coin cells. The SR44 is a high-capacity silver oxide cell with a 1.5 volt output. Being silver oxide, it doesn't contain toxic elements and is considered to be incinerable, so it's good for medical applications. If you take the datasheet capacity numbers, you could power this stimulation for about 13 hours. But given the relatively high current draw of 6 milliamps for this application, the battery capacity would need to be derated by about 50%. So you're down to 6 or 7 hours maximum for that battery. A similar analysis of the lithium-based CR2032 would give less than 50% of that datasheet figure. But the literature reports many variations on the treatment regimen, ranging from the continuous DC, which we showed earlier, for 24 hours a day, to pulsed currents of one 60-minute period or multiple shorter periods. So the exact detail of the application would have a major impact on the energy requirements for this relatively power-hungry application. Now, if you look at the application for thermoelectric energy harvesting for this, when you look at where dressings for hard-to-heal wounds might typically be deployed, you find an environment which is not readily accessible and often under clothing cover, be it on the lower trunk or the leg or even the base of the foot. And you're also frequently dealing with patients with reduced mobility and in environments with minimal opportunities for convection. So these are environments with very low thermal gradients, possibly of the order of only 1 or 2 degrees Kelvin. We've also seen a large variability in the heat flux from both between different individuals and across the age profiles. And these are all factors that do not readily lend themselves to thermoelectric generation harvesting. If you look at some of the commercial and even emerging TEG devices, you'll see that they all display both voltage and efficiency that are very low at low delta T's. And there is almost no characterization data presented for delta T's below about 5 degrees K. So the publication of this type of data would be one of the major requests from enables to the energy harvesting community. The closest application area for TEG would be that in the area of wearables. These are just typical examples. Here, the literature typically shows TEG integrated into wrist bracelets, sometimes with very large heat sinks, which would be especially unsuitable for wound dressing applications. So we'd like to see a focus on microwatts achieved with demonstrations in more applicable form factors. But even with these demonstrators, the levels of energy harvested are still in the low microwatt levels, which are inadequate for the power-hungry stimulation, but may be more appropriate to enhance battery life in dressings with passive sensing. So this could be a topic for a further TA program. So we'd pose a question to developers: what areas and form factors are realistic before you get into the area of diminishing returns? So in summary, this program was a great opportunity to bring about a thinking about power mentality into early discussions with the stakeholders and developers. In this particular opportunity, we needed to work with the clinicians and product developers to understand the desired dressing lifetime, not just the battery lifetime. The particular electrical stimulation treatment has possibly the largest impact on power, so we need to decide what's most relevant mode for these initial use cases and design the implementation accordingly. We also have to work with the clinicians to identify what are the most relevant wound parameters to monitor, as well as how often they need to be monitored and what work needs to be done on sensor development. So these discussions will allow the entire team to understand all the trade-offs and thus optimize power consumption. And working with the energy harvesting partners will ensure that opportunities for ambient energy are based on realistic form factors and temperature gradients, and finally aid the product developers to come up with the optimized design. And thanks for listening to me, and I'll hand over to Peter now.
Thank you, John. So I will share my screen. So now everybody should see my first slide.
Perfect.
So the next two use cases I like to introduce are actually use cases we realized out of the Enables program, but of course they can be a basis for upcoming new transnational projects. So the first use case I want to talk about is machine monitoring. In a lot of mechanical systems, the vibration is always available, and the vibration is typically or can be used as a measure of state of health. So if you consider machine pumps or even turbines, you always have some kind of vibration, and these vibrations are typically a hint for wear out. We can use this vibration to predict upcoming failures and predict also or avoid downtime by sophisticated maintenance. Of course, to measure these vibrations, sensors will be used on all these kind of mechanical systems. And the big challenge is to provide retrofitting sensors for these condition monitoring applications, because these sensors should be easy to install, and of course, they should be maintenance free. Of course, furthermore, you all know vibration and deformation can also be used for generating power. And so we can use these vibrations also to get rid of batteries and to provide power to these retrofitting sensors. On large equipment, the good news is that size and weight doesn't matter. So it doesn't matter how big your generator might be, because on these large mechanical systems, these generators do not really pose any harms. So our vision is to provide wireless self-powered sensors which measure the vibration levels and can predict potential failures or downtime. The key technology component I like to introduce today is a wideband piezoelectric harvester with a dedicated AC-DC converter, and these two components are used to power vibration sensors, and they are also used to power a wireless module to transmit that information to a nearby control center or base station. So what you see here is a low-cost, simple design of a piezoelectric harvester. So we are using off-the-shelf piezo discs, and on that off-the-shelf piezo disc, we have put a seismic mass. How you can see in the lower picture. The piezo is in the bottom side of this plastic housing, and we have a cavity below that piezo disc. And if we have a seismic mass on that disc and we mount everything on a vibrating object, on a motor, on a pump, then the seismic mass is pressing down the piezo and it's generating an AC voltage. The typical power output of this system presently is around 3 milliwatts with a 0.1 G excitation. The main property of this harvester is that it has a quite wide bandwidth of up to 12%. Of course, we always have to tune the center frequency of this harvester to the exciting source. So if we have a motor running at 50 Hertz, we have to tune that harvester to 50 Hertz. Together with that harvester, we are using a sophisticated AC-DC converter, which is actually optimized for a large input voltage range, because depending on the excitation level, these piezoelectric discs provide voltages between 1 and 50 or even 80 volts. And of course, to extract the maximum electric power out of that piezoelectric disc, we want to use the whole voltage range. And for that reason, we have to use an AC-DC converter with a very large input voltage range. So on the next slide, you see the system installed on one of our pumps in our institute. So my colleague here is using the whole system. This whole system is comprised of the piezoelectric harvester on the bottom side, the lower side. Then above the harvester, we have the seismic mast. And on the topper side of that black housing, we have integrated the AC-DC converter on a PCB together with a Bluetooth Low Energy module. And this Bluetooth Low Energy module uses the power of the piezoelectric vibration harvester and is completely self-powered by the vibration. So presently, this system can measure up to 8G, and it measures the vibration for around 20 milliseconds at a bandwidth of 800 Hertz and transmits that data over Bluetooth Low Energy. And you can use any kind of a PC or even smartphone with a Bluetooth connection to see the acceleration data and to see the acceleration level and the frequency. The second use case I like to introduce today is our smart screw connection. So as you all know, in numerous technical constructions, screw connections are widely used. So if you have a look at the pictures here, for example, these bridges use a lot of screws, or even these pipelines, or if you also consider turbines, screws are used everywhere. And these screws have to be monitored regularly. So a regular inspection is monitoring in all these applications. And in a lot of applications, we would get an advantage by a permanent monitoring screw connections. On the other hand, of course, the infrastructure powering of a data transfer of that screws is often missing. Furthermore, these screws could also be used for mounting additional sensors. Screws are an excellent and they are a standardized mechanical interface. And from the perspective of energy harvesting, screws also provide an excellent thermal conductivity. So our vision was to have a screw connection as a fully integrated IoT device, where we integrate sensors, the power supply, and the communication module. The key technology component of our smart screw connection is a wireless preload sensor with a solar or thermal power supply. So on the left upper picture, you see a washer, which is used together with the screw. And on this washer, we have a piezo resistive layer, which is used actually as a force sensor. We call this layer Diaforce. It's a product of another Fraunhofer Institute. And together with that piezo resistive layer, we have an additional structure which is used as a temperature sensor. And with that help of that piezoelectric layer, we are able to measure permanently the preload force of the screw connection. In the head of the screw, we have integrated a low power wide area network module, which is able to measure the preload data from the sensor and to transmit it over this LP1 system. We have an additional RFID interface in the screw for configuration and programming. And we have options with a thermoelectric generator, an option with a solar cell, and one option with a battery to power that whole electronics, so to power the sensor, power the wireless module, and data processing. Here we have some measurement results, and we have some examples for the application performance. So one option of the screw is using a thermoelectric generator, which uses the temperature difference in the head of the screw to generate an electrical power. You can see here, for example, with 4 kelvins, we are able to generate around 150 microwatts. And that's sufficient to power up these LP1 systems every couple of minutes. We're using a very optimized DC-DC converter, which has a very low cold start voltage. And with that converter, we are able to power up the whole systems with even very small thermal gradients. We have a sophisticated energy management integrated. so that depending on the available power, the transmission rate is automatically adapted. So if we have a lot of power, in terms of a lot of high thermal gradient, we can transmit more often. If we have only small thermal gradients available, the transmission rate is of course reduced. Presently, we have integrated everything in the housing of an M18 screw connection. And finally, you can see here some performance data. So in this table, for example, if we have a temperature difference between the thread of the screw and the head of 33 kelvins, we can transmit every 15 seconds. If we have a lower thermal difference, for example, 25 kelvins, we can transmit only 30 seconds, only every 30 seconds. Of course, if we have even lower thermal gradients, so down to 5 Kelvin, we can transmit every couple of minutes or a couple of hours, what is also often sufficient in the most of applications. We also have an option which operates with a solar cell. Also here some performance data, for example, with an outdoor light, which is comparable to 18,000 lux. We can send every 30 seconds. With an halogen lamp, which is typically indoor lighting, we have a transmission frequency of 45 seconds. Finally, we have also an option with a battery, which is a 230 milliampere hours battery. Also here, of course, depending on the transmission rate, the operation time of the battery is between 130 days for a transmission frequency of 2 minutes, up to 3 years for a transmission frequency of every 24 hours. With that final slide, I'd like to pass over to my colleague Gert.
Thank you, Peter. Hello, everybody. So I would like to go on with the presentation of the last two use cases. Hopefully you can see the slide.
Yes, everything.
Yep, that works. Yep.
Very good. Yeah, the first one is the coolant monitoring. We have here a look to a continuous casting line. That's for steel production. You see on the photo the big pot where the steel is heated up and is filled into this casting line. This sketch on the left side, you see the liquid steel is flowing in this line. And the most critical part here is the cooling down and the crystallization phase of the steel. That gives the quality. That takes place in this lower sketch here, where you have some nozzles. They are spraying the coolant onto the steel surface, on these steel slabs. So they have to be controlled. For this, we are thinking about these sensors. We have developed this kind of sensors to control the coolant. The coolant is a mixture of water and other liquids that is sprayed on the surface. The temperature of the steel and at this place is about 800 degrees C, but the place where the sensor sits behind the mixing unit is about 100 degrees C, a little bit higher perhaps, and there we'll do the measurement. So the idea is here the integration of a sensor that allows the control of temperature and pressure of the coolant to see that everything is fine. We have about 100 of these nozzles per casting line. So we need for one line about 100 of these sensors, and we have several of these lines in one plant. So the solution here we are targeting in is a system with self-sufficient sensors that controls these processes here. So how does it look like from the realization? We are using thermoelectric generators, the TEGs. So we are planning with temperature gradient of 10 degrees C or 10 Kelvin. different for the operation phase. We have to measure each second one value per nozzle. And we do it in this way that we have a housing that is mounted on the tube and an external sensor that's connected to a maintenance output of this tube that's connected by a screw there, and then with the cable to the electronics of the sensor. So the sensor can then operate with these electronics on the hot side. We have the air around, and the cold side is the coolant. You see the housing design here with these red arcs showing the heat flow or the cool flow through the thermoelectric generator. So that's the most critical thing to see that the energy flow is going through the TEG, so that you have enough power for this. A little bit back here, what's shown else, we have here the communication link. It's used the UHF ISM band at 868 megahertz, and we have a special protocol designed for this with 84 sensors per channel, so you can have several channels to operate one line. So the results shown here, the housing in the first photograph here with the clamping mechanism and the external sensor for the control, and the ruggedized housing here in this area. So we have neglected the heatsink part. We have only the surfaces of the housing. That's enough. We have typically enough temperature difference between the coolant and the ambient temperature, so that we can achieve a good operation. It's more than 20 degrees C. So here we have full operation at 80 degrees C. We need an average about 10 milliwatts in operation. We have here this housing. We have done operation for 6 months with a lot of sensors. You can see the behavior from startup. What we've done here is a special startup kind for setup. The first types we used additional battery to see how it's working. At the beginning, we are starting here with the temperatures. You see the delta is the green curve here of the delta temperature. That's sufficient, and you see the orange curve here. That's the changing of operation between battery and TEG. So we are starting in the cold operation with the battery to see how it's working and how it's starting, and changing if to the TEG if we have energy, and switching back if the energy is not sufficient. For example, if you are transferring protocol by wireless link, then it switches back, and this sees a little bit the behavior of the startup. That's only for characterization and testing, because the battery is not sufficient for the high temperature. For the real operation, it's removed, and we have the full TEG operation, of course. But it shows only the startup in a let's say cold phase. Okay, so for this use case, going to the next one from home automations, have a look to window sensor. Window sensor is not new. Everyone uses this for smart home applications, of course. But if you have a lot of windows and you have battery-powered sensors, this is a good example how to exchange it by maintenance-free sensors. We have here from the motivation, of course, the use of batteries. That's too much maintenance. We want to avoid this. There we are going to energy harvesting using the light, using photovoltaic cells, solar cells. And we are also doing a little bit more on sensor side. You see in this lower picture here many functions: the tilting detection, open close, of course, the position of handle, the light intensity, temperature, humidity, bounce, something is coming against the window. We have some intrusion by drilling, by smashing the window pane. That might be also possible and might be detectable. So the idea is here to bring a sensor at the right position of a door or window and taking the energy from the light. So, and here the place of the device is important. There are also some sensors available which are solar powered, but often they are on the inner side and don't use or don't operate too safe in the darkness. So what did we do here? What did we do from the realization side? I mentioned already the photovoltaic cell as supply. We also added a MEMS multi-sensor with 3D acceleration, with 3D magnetic field strength. That's for the position, of course, and also for intrusion detection, and connecting the sensor by Bluetooth mesh. We have here this more on a high level, this block diagram. Not more is necessary, but you have to select the right things to have these very low power available. We are putting the sensor close to the window panes. So here we are measuring then with the magnetic field strength and the acceleration, also the position and open and close. I know in Europe we have different ways to open a window. This is the German, and in some other countries most used way to open it in this way, and to recognize us with this sensors. So we have these functions: recognition, vertical opening, and horizontal opening. So the results from this are we have with our sensors a detection of knocking, levering, hitting a ball, for example. Glass breakage is detected, and also drilling. We have also the position of closed, tilted, regular, opened. So from the energy management, we have planned in this that we have at least 24 hours operation in darkness. For this, we need an energy of 420 milliwatt seconds, or in other words, what we need is to build it up is 3 square centimeters of cell for this realization, and a special cap for storing for the darkness of 390 millifarad. So this is from the realization of the energy side, and we are putting the sensor on this special place between the panes of the window from insulation glass. So this can be included during production of the glass. So it's completely covered, and there's no way to manipulate it. You have no wires, and you have also light available in most of the positions and have a good operation. So the energy harvesting starts at about 50 lux of light intensity going to this solar panels. So in the moment, the sensor is rather, I would not say big, but it has the size of about 4 times 1.5 centimeters and 0.7 in height, and it's put on the spacer for these panes. In future, it has to be a little bit smaller. From the volume, the size is okay, but from the shape, it has to be modified a little bit. So the idea is with better and more reduced energy consumption of the parts, to have also smaller components available, and it's yeah, more or less invisible in this area. So then thank you very much. I think we are just in time. Hopefully we have some time for answering questions.
That's great. Thanks for that, Gerd. Many thanks. Okay, so I hope that was a good insight to many of the practical use cases we have for energy harvesting. I hope that this might inspire some people in the audience to approach us enables and to do some transnational access feasibility studies. If you've got some ideas there, we would love to hear from you. So we can do metrology, we can do characterization, we can build some early prototypes, we can understand what are the opportunities for optimizing the power consumption of your device. How, at the very least, how can we maximize battery life, and in some cases, maybe even get indefinite power using the ambient energies that are available. So, Paul, I believe we've had a couple of questions. Do you want to just maybe call out the questions, and we'll try and answer them amongst the presenters?
Yeah, I think Nicholas is back with us, and he has them there.
All right. Okay. Let Nicholas host it.
I can do it. Yeah, I can show them on the screen, or do you want to prefer? Yeah, I'll show the ones that we have received on the registration.
Okay.
Sorry, if I can. I hope I'm able to show you.
Okay. Okay.
Can you
Thanks
see
for that,
that?
Nicholas. Yeah, we can see it. Yeah. Yep. So I'm aware of the fact that we're just coming up to the hour now, so we'll stay as long as people are willing to listen. But you know, people are welcome to stay on beyond the hour, and we'll have this all recorded as well. So if anybody misses the tail end of this, it will be available in the recording. But I'm hoping as many of you as possible can stay on for another few short minutes to hear the answers to these questions. All right, we'll take the questions as we have them. So the first one is, what is the status of energy harvesting for biomedical implants? So, John, you're the obvious victim here.
That, Mike.
Yeah.
Yeah, but medical implants are very, very interesting area. There's many unique and interdisciplinary issues such as materials and biocompatibility. There's also a big crossover with research into really useful biosensors and ultra-low power electronics, such as ultra-low power radio. So we've seen piezoelectric used quite a bit, but in research papers with piezoelectric used for extracting energy, say from motion in artificial joints and from motion in heart muscle, and even in movement of the diaphragm connected with breathing. We've also seen piezoelectric used in combination with a MEMS receiver for being part of an energy transfer system using ultrasound. We've even seen work on embedded photovoltaics, where you get near infrared transmitted through the skin to power this embedded PV. There's also a lot of work in wireless power transfer, and even some work recently reported on embedded biofuel cells powered by glucose. We've also seen an interesting one, which is an endocochlear implant in the ear, powered by the tiny biological battery in the inner ear, which is very analogous to the skin battery that I mentioned in my presentation earlier. But to what extent these are still ideas in the laboratory or have gone through clinical trials, I couldn't really comment. But in this area, the entry barrier is really high, mainly due to regulatory issues. So you'd expect the market to be dominated by the indigenous companies that are already working in the area.
That's great, John. Very comprehensive answer.
Something. Yeah, thank you, John. One comment to this. We are working at IMS also on human implants. That means integrated sensors into the human body. Checking also the energy harvesting as technology. We have two solutions which also might be used. One is RF harvesting. From the side of RF harvesting, we have some solutions for this. There's already one in a product. For this, this will be presented in our next webinar in April. We have then The RF harvesting and inductive coupling for energy harvesting use cases and the technologies there. Please have a look to this. So this is a short commercial for the next webinar. And the second technology is ultrasonic energy transfer that works also for power consumption, for power transfer into the human body. These are techniques, both technologies using the wave from outside into the body. That means it has to be controlled from outside. You need something that brings the energy into the body.
That's great. Thanks for that, Gerd. So I think very good answers there. Again, in the interest of time, we have six or seven questions to go through. If anybody wants further information, please contact any one of the authors offline, or just come into us at Enables, and we'll happily give you more comprehensive information. Okay, second question there is what are energy harvesting techniques for smart dust applications? So hopefully most people are familiar with the concept of smart dust, but for those who aren't, this is kind of a concept that originally came out of Berkeley, I think maybe back in the 90s, the whole idea of kind of MEMS scale wireless IoT devices, and has been further enhanced by various people, including, for example, the University of Michigan. They've got what they call the Michigan moat. So it's all about trying to come up with these tiny sensors that we can kind of deploy and forget for many applications. So we could talk for an hour about the various types of energy harvesting techniques, but I'll try and give you a very brief flavor of the kind of things we can do. And I guess that the very short answer is that it really depends on the ambient energy that's available. So for example, if we're deploying widespread sensors, for example, in an outdoor environment, for example, for an agri-tech application, we're monitoring soil, or we're monitoring weather or crops or the environment. Obviously, solar is the obvious one to use there. So, for example, the people in Michigan have devised an energy harvesting device which is only 1 millimeter by 1 millimeter of a solar panel, which is enough to power their tiny moats. In other applications, if we've got some heat from a machine or a body from, for example, for Industry 4.0 or from medtech applications, there are opportunities to do some thermoelectric energy harvesting there as well. In terms of vibrational harvesting, again, it depends on the size of the device, but what we have seen is that the two, I guess, main competing vibrational types of technologies are we have electromagnetic energy harvesting, and then we've got piezoelectric. There's also electrostatic, but let's not get into that for now. What we've generally seen is that the piezo energy harvesting is more conducive to miniaturization. So I think we'll see more of the piezo type devices rather than the electromagnetic devices, for the very, very small applications. The electromagnetic ones can deliver significantly more power than the piezo devices, and indeed some of the use cases you saw there use the electromagnetic rather than piezoelectric devices, but electromagnetic is not really scalable for small applications. So that's a very quick snapshot as to the kind of energy harvesting techniques and technologies are out there. Again, short answer is it very much depends on the application. So if somebody has a particular application in mind, we'd be very happy to go into further detail there and try and give you a feeling for what ambient energies might be possible. And indeed, several of the TAs that we're doing, transnational access programs and enables, cover that very topic. Somebody comes to us and says, I've got a particular type of application. Can you please do an assessment for us as to what are the ambient energies that are potentially available to us? Okay, so food for thought there. Right. I move on to the third question then. How mature are products to apply as building blocks to an IT use case? So maybe either Peter or Gerd might want to take that one.
Yes, sure. I can say a couple of words. So actually, the main components are very mature. I would say you can build your DC-DC converter with off-the-shelf chips, with off-the-shelf transistors. You can buy the thermoelectric harvester. You can buy the solar cells. Of course, the main product integration, so putting it together with a wireless sensor and so on. This is a matter design. So as you have seen from my examples or from the examples of Gerd, the system integration into a final product, of course, this is a lot of work to do, but anyhow, the main components are available, at least in terms of thermal harvesting, in terms of solar harvesting. There are even some electrodynamic generators available as off-the-shelf components, and they can be used as a building block for an IoT use case.
Okay, very good. Thanks, Pete, for that. Okay, Gerd, do you want to add anything to that, or we try another question?
Yes, that's nothing to add from my side. It's completely right what Peter said. It's an individual engineering task, putting the components together, also together with software. That's what has to be done individually for each use case.
Okay, thanks for that, Gerd. Okay, so let's try and finish this out in the next few minutes, seeing as we are over the hour. So the next two questions are the minimal size of energy harvesting solutions and applications and the type of energy source. I'd like to think I've kind of answered that when we talked about the smart dust applications, that, that some devices, give us nice amounts of power if we have a decent ambient energy. So for example, thermoelectric devices give us tens of milliwatts or even hundreds of milliwatts of energy if the temperature gradient is high enough. Similarly, electromagnetic vibration devices can give us a decent several tens of milliwatts of power if there's a decent enough vibration there. When we go to miniaturize, then there are different challenges. Solar energy is solar panels are typically linear in terms of the size versus the amount of power that they generate, and then we have the piezo devices, which are particularly good for small applications. So we can certainly go down to the millimeter scale. One of the big challenges is, can we go down to the I suppose down to the NEMS level for energy harvesting? And the answer is yes, but to what extent then can we add these energy harvesting sources together to come up with enough power to power a device? Okay. The last two questions, then I'll make a stab at these, and then I'll leave the final word to John, to Gerd, and to Peter. The questions relate to the DC power collected by such solutions and the power conversion techniques. Now, I think DC, you should be remembered that we not only get DC power, but very often we get AC power from some of the sources as well. For example, vibrational. DC power does come from thermoelectric energy and from solar energy, but vibrational can be AC. And therein lies some of the problems, that we need to convert this energy, and very often they're at very low voltages and very low currents, or in some cases, for example, electrostatic, we can have very, very high voltages but very high impedances. So we've got to convert these to usable volts and amps, and that means there are significant power management challenges converting these to what we call usable power or usable energy. And therein lies a lot of the research opportunities for many of us in Enables. How do we come up with circuits which can efficiently convert these power levels? We in Tyndall, for example, have developed a power management IC which can go all the way down to less than 1 microwatt in power. Most off-the-shelf devices need several tens of microwatts before they can give any kind of reasonable output power at any kind of reasonable efficiency, more than 50%. What we've done, for example, in Tyndall is we've come up with a configurable power management IC solution whereby we can adjust the configuration mode of the converter so we can either step up or step down the voltage with pretty high efficiency using high frequency switching techniques. So hopefully food for thought there for anybody who's interested in this area. This is one of the biggest challenges. How do we efficiently convert the very small amounts of ambient energies with sometimes awkward volts and amps and impedances to usable levels? Again, go onto our website and you'll find more information regarding some of the technologies that we have there and the kind of performance levels that we have. So with that, I'll invite John or Gerd or Peter to add to I've tried to compound 3 or 4 questions there together with an answer. So anything that you guys want to add to the questions there?
Yes, one remark. showing the wide range of power, what's possible in these applications. On the lower side, there's one example where you can be extremely small. Consider an application with RFID. RFID, for example, uses works in the area of microwatt. That means 1 volt, 1 or 2 microamps operation of an RFID tag and the size of a square millimeter. What we are doing there, for example, is putting a solar cell on it, only a square millimeter, but that helps to have enough power for the operation, don't needing the RF harvesting, and increasing the reading range ×4, for example. That's the very low power application. On the other side, we have also with solar power higher power applications operating, not in continuous mode, but operating for some time, a compressor pushing some air on into a special application. For this, you need 24 volts and 6 amps. So we have a lot of power, and this can be handled also with, of course, energy harvesting techniques using a solar panel of some 10 square centimeters, and of course, storage elements necessary for this. So that shows a little bit the wide range. I think in other applications it's the same, depending on the conditions around of the environment. You have many possibilities. Okay.
Thanks, Gerd. Okay, Peter?
No additions from my side. Thanks.
All right. Okay. All right. Okay. Very good. Good. Okay. So I think that's pretty much it. Again, if anybody wants more comprehensive answers than what we've given there, we're more than happy to talk to people offline. We can contact us via the website, contact us via emails and so on. Paul or Nicholas, do you want to do just a very quick plug of our next webinar before we close up, and thank everybody for their attendance today? Do we have a date confirmed?
Well, thank you. Definitely, obviously, thanks everybody for attending, and especially the people who stayed for almost 75 minutes. So that's great. To see we had a big crowd that day after the 60 minutes, but obviously some people had to drop. So again, if you have any questions for the speakers and so on, just send it to us and we'll try to respond. The webinar has been recorded, so you want to check some of the details, it will be uploaded to the website in the next couple of days, so you'll be able to go over it and check any details that you could have missed on the live presentation. I'm afraid I don't have the details of the next webinar. So, Paul, do you have those? Or?
Paul or Gerd or Peter, do you have the details for the next? Have you got a date yet for the next one?
I don't.
No.
I have nothing.
All right.
Sorry.
Okay, no harm. So everybody,
Again,
please
keep an eye on the
watch this
website.
space. We'll send out details to everybody on the mailing list here, and we'll make you aware when the next one is. It's about wireless power transfer, which I think is very interesting for many, particularly medtech applications, as Gerd and Peter talked about. The idea of having an infrastructure in place and wirelessly transferring power. For example, for wearables or for implants for patients in hospitals, and keeping the batteries in them topped up so that the patient doesn't have to worry about it, or indeed the doctor. Okay, I think we better wrap up with that. So thanks for such a great audience and for participation. Some very interesting questions there. And the Enables program, Transnational Access program, will be open until the end of the year. So our doors are still open to do these free of charge studies. For anybody who's interested, the process is very, very simple. You just need to sign up to Enables, and then 4 or 5 lines to create an inquiry, and we'll assign somebody to work with you on writing a very simple proposal and getting up to maybe 6 to 8 weeks of free of charge studies done by any one of the Enables Access partners to do these studies for you. So thanks everybody for joining us, and we look forward to seeing great attendance again at the next webinar. Thanks everybody.
Bye-bye.
Thanks.
Bye-bye.
Take care.
Thank you.
Thanks,
Bye-bye.
Mike.
Bye-bye.
Bye, everyone. Bye.
Bye-bye.